numerical calculus, we have talked about interpolation, differentiation, integration, and ordinary differential equations. So now we are entering the last part of numerical calculus, that is the partial differential equation. So in this week, we'll talk about numerical solution of partial differential equation. And in next week, we'll talk more about application problems using ordinary as well as partial differential equation. In this lecture, we'll talk about the classification of partial differential equations and some of the equations which are important for engineers. We'll take a look into it. Let's start with a differentiable function u, which is a function of two independent variables x and y. A first order partial differential equation will be something like this. This will be a function of u, x, y, partial derivative of u with respect to x, and partial derivative of u with respect to y. Similarly, in a second order PD of u, we have a function of u, x, y, then the first derivatives of u, and then the second derivatives of u. Second derivatives will have one del 2u del x2, another del 2y del y2, and there will be one cross derivative del 2y del x del y. In the same manner, we can define third order, fourth order, etc. So in general, nth order partial differential equation of u will be given by a function of u, x, y, then the first derivatives, second derivatives, and then third derivatives, fourth derivatives, etc. nth derivatives to include lot of cross derivative terms. To simplify this notation, we sometimes use this ux, uy like this. U subscript x actually means del u del y x. Similarly, u subscript y means del u del y, etc. It doesn't change in any manner the differential equation. It only looks slim. Now, this definition of partial differential equation can be generalized for independent variables greater than 2. Here we are talking about independent variable x and y, but we can have m independent variables x1, x2, x3, etc., etc. up to xm. As long as m greater than 1, this is a partial differential equation. In this course, of course, we will not go very far. We will discuss only second order partial differential equation because they are important in many branches of engineering. And we will see only up to time plus 3 spatial dimension x, y, z and time t. So at most we can have 4 independent variables, but we will probably not talk about 4 independent variables. We'll try to confine ourselves 2 to 3 independent variables. So let us take a PDE of u, that is f of u is equal to some function of x and y. Here this f of u is a multiplied by uxx, which means double derivative of u with respect to x, plus b multiplied by uxy, double derivative of u with respect to x and y, etc., etc., up to c u y y dux e u y plus f u. Here u we have taken as a function of only x and y, 2 independent variables. This a, b, c, d, e, f, they may or may not be constant, that we don't know yet. But this equation, we will call it homogeneous if this function of x and y is 0. So each term have u that makes the equation homogeneous. Otherwise, this equation is non-homogeneous. This equation is linear if we have f of certain variable u1 plus f of another variable u2, if I add them up, I get f of u1 plus u2. And also, if I take this variable u and multiply with a scalar a, then f of au is equal to a multiplied by f of u. If this condition is not satisfied, then we call the equation nonlinear. Another way to look at linearity is that in this PD fu equals gxy, if all these terms a, b, c, d, e, f are either constant or function of independent variables only, then this equation you will see that they will turn out to be linear. This is an easy way to check linearity. If this condition is not satisfied, the equations will be nonlinear. Now let us take up a nonlinear partial differential equation. Here this is a uxx plus b uxy plus c uyy etc. up to g equals 0. This type of partial differential equation is also called quasi-linear with respect to second derivative if a, b, c are either constant or functions of x and y only, but d, e, f are functions of x, y, u as well as first derivative, which means this quasi-linearity is that the highest order of derivative, they are sort of linear, but then the lower derivatives, they may have certain nonlinearities. In short, in a linear PD, the unknown u is not multiplied with u or its derivative. If it is, then the equation could be nonlinear, and a particular case that is quasi-linear. This is important in distinction because in some cases the quasi-linear equations are slightly easier to solve. Of course, the idea of nonlinearity, homogeneity like concepts can be extended to higher order PDEs as well as PDEs with more than two independent variables. There is a serious distinction between PDE and ODEs. In PD, very few PDEs have analytical solutions, and whenever we have analytical solutions, you will find those PDEs are linear. PDEs are super sensitive to initial conditions, boundary conditions, unlike ODE. In ODE, these initial conditions, boundary conditions, they play a passive role. We solve the equation, and because there is some constant, we get the value of constant using initial boundary conditions in case of an ODE. But in PD, initial and boundary conditions, they will dictate the nature of the solution. They will also dictate the kind of error that the solution will produce. And they will also dictate if at all there will be a solution or not. So the role of boundary condition, initial condition is much serious as compared to that in ODE. Similarly, you will see that in PDE, you have lines of discontinuity. This is not an usual thing, but you will see that in supersonic flow, there are lines of discontinuity. In wave propagation, there are lines of discontinuity, and solution of PDE can produce discontinuous lines. In ODE, these are not seen. Everything will be continuous in ODE. So these are some of the unusual characteristics of PDE as compared to ODEs. Now, several PDEs are very important for engineers, and in this course we will particularly talk about heat conduction equation. Heat conduction equation is this time derivative of temperature T is equal to alpha del square T, where alpha is a property we call thermal diffusivity. Del square is a mathematical operator. We call this Laplacian. It means del square T means del 2T del x2, del 2T del y2, del 2T del z2. This alpha is K by rho C, where K is the thermal conductivity, rho is the density, and C is the specific heat. This Q triple prime is the volumetric heat generation rate. Now, you may not be interested in heat transfer, you may not know heat transfer at all, and that is not a problem in this course. We'll talk about this kind of equation. This kind of equations are important in many fields of science and engineering, including heat transfer, mass transfer, fluid mechanics, electrical engineering, and many other branches. This equation is also used to calculate the propagation of certain species, including the human migration. Similar to the heat conduction equation, which also we call diffusion equation, similar to this diffusion equation, we have this incompressible mass conservation and incompressible momentum conservation equation. We will not talk about these equations in this course, but these equations are extremely important for engineers, especially mechanical engineers, aerospace engineers, chemical engineers, civil engineers. They deal with these equations. Solution of this equation, they consist of a different subject which is called computational fluid dynamics. Here this is a del dot u, that is divergence of this u, that is velocity vector of fluid, and that is equal to 0 for incompressible mass conservation. Similarly, the momentum conservation is this del u del t plus del dot u is equal to g minus 1 by rho del p. This is the pressure. Then nu del square u, this is the viscous term, and there, if there is some momentum source. Similar to this momentum conservation, there is also energy conservation. This diffusion equation which we are showing here, this is an energy conservation. This is a case where there is no velocity in the continuum, but if there is a velocity, for example, a fluid is flowing and there is a convection going on, then the equation will be like this del t plus del dot ut, that is the convective part, is equal to very similar alpha del square t and st, a source term. Here this alpha is again thermal diffusivity and nu is the kinematic viscosity. Now I understand that some of you may be interested about this equation, some of you may not be, but that really doesn't matter. These are only examples of some important equations for engineers which are given in partial differential equation. Although in this course we'll talk quite a bit about this conduction equation, or what we call diffusion equation, and how we solve it. This is an equation that is relatively easy to solve, therefore we will talk about it. Now, based on the physical problem, we can classify partial differential equation in different ways. The first one is the marching problem, which gives us evolution of something in time. So this is called evolution problem, propagation problem, as well as transient problem, where something is changing in time. So for example, this is a typical diffusion equation. This is used in heat conduction. This is also used in diffusion mass transfer, as well as here in this equation del u del t equals alpha del to u. This alpha is greater than 0. Here u marches in time, that means evolves in time, and also propagates in space. What does that mean specifically? We will see later on with example. What constitutes a marching problem is that at time t equals t naught, the value of u depends on whatever the value of u at time t less than t naughts, but not on the value of u t greater than t naught, which means the present value depends on past and not on future. Now this sounds very obvious, but mathematically it is not so. So for instance, let us say this equilibrium problem. This is another extremely important problem in engineering, that is del to u equals 0. Here the Laplacian of u is 0. This is called Laplace equation, or Laplacian of u is a function of independent variables, that is the Poisson equation. Both Laplace equation and Poisson equation, they indicate equilibrium problem or steady state problem. Here u at any location depends on u at all other locations. So this is fundamentally very different than the marching problem. The third type of problem is eigenvalue problem, where we have equations like this: del 2 u equals lambda u. You remember from linear algebra, this lambda is like eigenvalue, and with homogeneous boundary conditions. So in boundary we have certain function of u is 0. So if, let us say, simplest case is u to be 0 at boundary, with u 0 at boundary and del 2 u equals lambda u, we know that a trivial solution of u equals 0 will exist. But this particular problem deals with non-trivial solutions of u. For certain lambda, we will have non-trivial solutions of u. And just like in linear algebra, in eigenvalue problem, we do the same thing. Here also, we try to figure out those non-trivial solutions. This kind of problem often appears in stability. The stability problems could be stability of a beam, buckling of a column, as well as stability in fluid mechanics or stability in a chemical reaction, as well as in many other areas of stability. Now we take up certain second order partial differential equation. So we have this a u xx, b u xy plus c u yy d ux, etc., etc. It will have typical boundary condition of a u x plus b u y plus c u plus d equals 0. And because this is a second order partial differential equation, this a may contain some second derivative, first derivative, etc., but it cannot contain a third or higher derivative. And same is true for b, c, d, etc. This type of equations have one more classification. If this b square minus 4ac equals 0, then we call these are parabolic. And if they are greater than 0, they become hyperbolic. And these type of problems are generally both marching problem. In engineering application, we have parabolic problem, for instance, in heat conduction. We have hyperbolic problems where the propagation goes at finite speed and it creates discontinuity. So this very common hyperbolic problem is wave propagation problem, supersonic flow problem. Similarly, this b square minus 4ac less than 0 is elliptic problem, which are, as we have already discussed, this equilibrium problem or steady state problem. Now, depending upon this a, b, c, d, e, f, their nature, this b square minus 4ac may vary at different points in the location where we are solving it, as well as they may vary in time. If a, b, c are constants, then they will not vary. Then we can classify the PD initially. But here, if for instance, a, b, c, they are functions of u, as we solve, the b square minus 4ac will evolve. And the nature of the partial differential equation will change, continue to change in time and space as we solve the system. And that creates additional complexities in PD solutions. Of course, in this course, we will take this to be constant and we will not get into all these complexities. Now, to summarize, we have covered some preliminary definitions, classifications, and some PDs which are important for engineers. We have introduced them. For your exercise, you take up this second order PD and you convert it into a system of first order PDs. This is something that you know how to do it from the exercises in ordinary differential equation. And then you can also use your textbook and study the PD classifications specifically from their different types of PDs and their examples. So that's all for this lecture. Thank you, and I'll see you in next class.